Okay, I think we can get started. Any questions from anyone before we get going on stuff? Final project questions, logistical questions, final report questions, anything of that variety? Things seem to be coming together pretty well in lab. Some of the projects are really cool. Once all the pages are posted, I'll send everybody a link so you can poke through everybody's projects and see what other folks have been working on. There's quite a bit of diversity this particular semester. So what I thought I'd talk about today, is there anyone in this class except for Aiden who's in the IoT class in mechanical engineering? Okay, great. So this is only going to be deja vu then for Aiden. Each year I give one lecture in that class about power management. Most of the projects in that course are, remotely deployed IoT devices powered by a battery. And in such an application, you care a lot, for instance, about how long your battery lasts. And so this is a talk that I prepared with that as the intended audience, that class as the intended audience, that summarizes an approach by which you can try to minimize your power in these systems. But I thought it might be of interest for some folks in here too. People are working on some battery-powered devices for which you might care about battery longevity, and so we'll talk about it. There's some interesting power-saving features on the RP2040 specifically that I thought I'd direct you to. And then we'll talk through a more general sort of device-agnostic approach to how one might try to minimize power in a system like this. So if you're trying to maximize your battery life, what you're really trying to do is spend your energy as wisely as you can. That implies, as we'll discuss, probably a sleep-wake cycle kind of software architecture as opposed to the alternative that I'll describe, which is a more sort of polling kind of setup. Basically, you want to keep the system as close to off for as much of all time as possible. Wake it up as infrequently as you can manage for your particular application. Do whatever it is that you have to do when you're awake as quickly as you can. Take a measurement or, I don't know, pull a sensor or move an actuator or whatever, and then get back to sleep as fast as you can. And so minimizing your total average power consumption involves first of all, trying to get your low power mode as low power as you can manage. So when the system is off or asleep or in its low power state, trying to drop that as low as you possibly can. Trying to wake the system intelligently. So that is to say, you're trying to synchronize your device with whatever it is that your device is trying to interact with or trying to measure. If you only care to take a measurement when someone opens a door, for instance, it's nice to turn your system on when the door opens as opposed to waking up every 1 minute and checking if the door's open, just as a for instance. But we'll talk through some other examples of that. And then once you're awake, you want to get back to sleep as quickly as you can. So this implies that some of the techniques that we've spent some time talking about in class this semester would be of relevance here. So, offloading stuff to peripherals so that you can accomplish tasks in parallel, and trying to basically keep your power consumption as low as you can while you're awake would be the other part of this. And then in addition to spending energy wisely, in the event that the device you're deploying includes some mechanism for energy gathering, I don't know, solar panels or whatever it may be, then of course this would enter the equation as well. But we'll get to that if we talk to it, or if we have time for it. The first thing I want to talk about is just organizing your program for energy efficiency. This is perhaps an obvious point, but let's suppose that, for instance, you're deploying some sort of an IoT device, some deployed battery-powered device that is going to take a temperature measurement every 10 minutes or something. You could accomplish that in two ways. At least two ways. One of the ways that you could accomplish this is you could have a while one loop spinning, and within that tight loop, you are always checking the value of some incrementing timer. So on the RP2040, for instance, maybe it's the case that you want to take a measurement every 10 minutes, and so you repeatedly check the state of that microsecond timer to see if 10 minutes have elapsed as measured by that timer. And once 10 minutes have elapsed, you take that measurement, communicate it out by whatever channel, and then you start polling that timer again to see if 10 more minutes have elapsed. That works, of course. That accomplishes what it is that you're trying to accomplish. The perhaps obvious cost of this is that even when your device is not doing anything useful, it's just measuring the passage of time, it's fully awake. All your peripherals are on, your CPUs are running, and you're constantly checking this timer to see whether or not you should take a measurement. In other words, the amount of power that you're consuming when you aren't doing the thing that you have designed the system to do, take the measurement and communicate, is about equal to the amounts of power that you're consuming when you are doing that. So you're almost always consuming the same amount of power because everything's basically on the whole time. Alternatively, if possible, it's nice to set up these systems so that rather than, let's say, for instance, you want to take a measurement every 10 minutes, an alternative would be you put the system into an ultra low power mode, as low as you can manage with whatever microcontroller it is that you're using. So that implies turning off every peripheral. It perhaps implies turning off clocks even. Turn off as much as you possibly can, and you only leave on the minimum amount of peripherals that you require in order to measure time passing and then to wake the system back up. In the case of the RP2040, it turns out you can do this, for instance, with a real-time clock. So you can turn off the whole system. Only the real-time clock is still on. That consumes very little power. It measures off 10 minutes, and once 10 minutes has passed, it wakes up the rest of the system so that the processors turn on, you gather a measurement, again, as quickly as you can, and then you go back into this ultra-low power mode. The advantage of this, again, perhaps obviously, is now, rather than always consuming a relatively constant amount of power for all time, you're in these two modes, and in those two modes, your power consumption is extremely different. So when you're in this low power mode, you're consuming some PS amount of power, which is maybe down in like the microwatts, right, if you're really, really good at this. And the idea is that you're spending almost all of your time in that mode. So if alpha in this little weighted average equation represents the fraction of all time that you are awake, right? If you're taking a measurement every 5 minutes and it takes you, let's be conservative and say it takes you, I don't know, half a second to gather a measurement, that means you're spending 99.999, however many % of your time in this ultra low power state. The consequence being that rather than consuming a constant amount of power, you're consuming this weighted average amount of power, where the notion is you're trying to make alpha as small as you can, spend as little time awake as you possibly can, and you're trying to make P sub s, the amount of power that you're consuming when you're asleep, as low as you possibly can. And of course, you're also trying to minimize this, right? But of course, when you're actually doing stuff, things are on, you're consuming power. But the exercise really is trying to drive that low power mode as low as you can possibly drive it. Are there questions about that? If that's, perhaps that's obvious to folks, but it's one of these things that's maybe worth just articulating. So I'd like to talk about how to do this, and the first part of this conversation that I'd like to have is, let's think specifically about this low power mode power consumption. How do we get that as low as we possibly can? I'm going to describe a strategy that I've used in the past and that I like. I'm sure that different people have different approaches to how to do this. But the way that I like to approach this is the first thing that I always do if I'm trying to get a microcontroller into a low power mode is read the relevant section of the data sheet for that microcontroller. And there will be a table somewhere in that data sheet that describes the power consumption of that device in various modes, and will also describe the power consumption of each of the peripherals on that device. So just to give you a couple examples, these are, of course, the RP2040. The CC1310 is another one I've worked with in the past. And if we open up the data sheet for this, let's see, I'm sure that we can find power consumption summary. So if we click this, we will find a table. And what this table tells us is, in various operational modes, how much current should we expect for this microcontroller to be pulling. And as you can see, in say, standby mode, right, the third row down there, with the real-time clock, RAM, with the real-time clock, CPU, RAM, and partial register retention, we should expect to be consuming 0.7 microamps. By the way, the CC1310 is designed to be a very, very low power microcontroller. So these are remarkably tiny numbers. But this is useful because it shows you, this particular microcontroller also has a built-in radio, which is what these radio TX and RXs are implying. But it shows you, if you're transmitting over the radio with this particular modulation and this particular power, how much current should you expect to consume while you're doing that? And furthermore, there's even some information here about how much current we should expect to consume from these various peripherals that we might have on. The UART peripheral, for instance, with its clock enable and the module idle, we should expect for that to be consuming 164 microamps. So generally speaking, in all of these data sheets, this information lives there someplace that tells you, in your various modes with various peripherals on, how much current should you expect to be pulling. So that's what the data sheet looks like for the CC1310. And of course, if we poke into the RP2040's data sheet, we should expect to find some similar stuff. Let's see, there's a section here, if I remember correctly, on power management. Oh, so here's power control. We'll come back to that in a moment. But I'll bet down maybe in the appendices. Oh, thermal power consumption. Here is a similar table that is showing you current consumption for each of the peripherals which you may have on. Notice this table is kind of interesting. The units are not microamps, but instead microamps per megahertz, which suggests that dropping your clock rate reduces your power consumption. That's worth knowing, right? So it's showing you that, for a given number of megahertz, you can figure out how many microamps you should expect to be drawing for each of these peripherals. Drop your clock rate so that the megahertz goes down a little bit, and these numbers would change. Trying to think if there's anything else I want to point out about this. So in short, this information will live regardless of the device you happen to be using. It's certainly the case that somewhere in that data sheet you can find this information. So then how do you actually use this? An approach that I like to take is the data sheet tells you how well you can expect to do. The next step of this process is you attempt to actually put that microcontroller into a low power mode and measure the amount of current that it's pulling by way of an ammeter or one of these devices that will measure, current down to microamps or picoamps or whatever. And you compare the amount of current that you are measuring against the amount of current that the data sheet says you should be pulling. Almost certainly it will be the case the first time that you do this that there's a difference there. You will be pulling more current than the data sheet says you should be. And then the exercise is trying to track down where the current's going, which is it's a fun exercise. Sometimes it's the case that the current is going to peripherals that you have accidentally left on in the microcontroller. Perhaps there's some that are on by default, and if you don't explicitly turn them off, they remain on, drawing current. Those can be a little bit hard to find, right? So you want to make sure you have everything off that should be off. It may alternatively be the case that your microcontroller is on a breadboard and you have some other circuitry around the microcontroller, and perhaps it's the case that your current is leaking through that. I've had the experience, I told this story in the IoT class, but in grad school I was trying to put this device into a really, really low power mode. And so I was going through this process. I knew how much current I should expect to measure given the peripherals and the external stuff that I had on. And I was measuring, I'm trying to remember how much it was. I think it was 30 microamps too much current. I couldn't track it down. And then I noticed that if I unplugged the I2C lines from the microcontroller, the ammeter went boop to exactly where it should be. The reason for this is I had turned off that external device, the I2C device, but as you're all aware from Lab 3, an I2C communication channel has pull-up resistors. When the device was turned off, it acted like it was a source of high resistance but not infinite resistance. And so a little bit of current could leak through those pulled up resistors through the device down to ground. And so that's where that leaky 30 microamps was going. The solution in that particular example was I ended up putting the whole sensor upstream of a transistor so that when I wanted to turn the device off by way of the microcontroller, I would do so. So when you configure it off, it was behaving as if effectively what you were doing was removing power, basically grounding the thing out. By putting it upstream of a transistor, I could turn it off by eliminating the voltage potential across it by bringing ground up to VCC. The consequence of that was there was no longer a potential difference across those pull-up resistors rather, and the leaky current went away. It's a solution that's okay in like these really, really low power electronics. You wouldn't want to wire an attic of a house like that, right? Yeah, so you figure out what you can accomplish, what you should be able to accomplish. You try to do that. You will probably find a difference in the amount of current that you're consuming versus the amount that you expect. And then you try to track it down. It might be inside stuff, peripherals you've left on. It might be external stuff that's leaking in sneaky ways. And you keep doing this, keep iterating until you get the two to match. Again, I find this to be a very fun process. This is kind of like, in the Galton board lab where you get obsessive about trying to optimize for speed. This tickles from the same kind of part of my brain, right? It's a fun kind of little puzzle to try to track down these little microamps that are leaking all over the place. Questions about this or thoughts? It's a little bit counterintuitive sometimes too, because the amount of current is so small that it starts to feel like, God, I'm stressing myself over like tens of microamps. But if you can have the amount of power that you're drawing in this low power state, and you're spending almost all your time in that state, then saving yourself a little bit of microamps in that state can extend your lifetime by a really, really large amount. And so it's really worth your time to try to keep that lower power state as low as you can possibly manage. And then of course you have to wake up. So you're in this low power state. How exactly do you wake up from that low power state? You essentially have two options. You can wake up by way of some internal signal. That is to say you've left some peripheral on in the device that is measuring the passage of time. And after a certain amount of time has passed, that peripheral has the ability to wake the whole system up. So in many microcontrollers, it is the case that you can, for instance, leave a timer on and turn everything else off. And that timer often has the ability to throw an interrupt that can wake up the whole system. That is true of the RP2040. On the RP2040, as I alluded to earlier, you can also do this by way of the real-time clock. We'll peek in the datasheet in just a moment, but the RP2040 has a sleep mode and then a mode that it calls dormant. In the dormant mode, everything's off. All the peripherals, except the real-time clock, the oscillators, everything is off. The only thing that is left on is the real-time clock. Because everything's off, that real-time clock actually needs an external oscillator. So this does imply that you need to power something external to keep the real-time clock ticking. But the frequency of that external oscillator can be as low as 1 hertz. And the real-time clock will continue to tick along, and after a programmed amount of time has passed, it will wake the whole system up. And we'll take a look at the datasheet in just a moment, but in that mode, your current consumption drops considerably, right? So you could have really, really long battery lifetimes. Or you wake up from some external signal. So it is often the case that you can turn the whole system off and only leave on a GPIO interrupt so that the system is off, except for this one little peripheral attached to a GPIO. And you've configured that such that when it sees a rising edge, for instance, it has the ability to throw an interrupt and wake the whole system up. So this is the solution that you really want to use if you're building an IoT device for which you only care about measurements when some event occurs. Maybe you, like I alluded to earlier, maybe you want to, I don't know, you have something in like a cabinet or something, and you only care to take a measurement when the cabinet door opens, rather than waking up every X number of minutes or seconds to see if the door's open. It would be a wiser idea to maybe you put a little piezo on the hinge so that it bends when the door opens, generates a little bit of current, which triggers a GPIO interrupt, which wakes the system up, so that your system is only awake when the event that you care to actually observe or measure or interact with in some way is occurring, and otherwise it's off. So in other words, you want to think carefully about how you are synchronizing your device with whatever it is that you're trying to measure. If what you're trying to measure is time-based, then that implies perhaps a timer of some variety. If it's event-based, then you might consider going through this thought process of, are there any clever ways by which I could synchronize my device with this process so that the process itself wakes me up when it starts? So with the internal signals, you got to keep something on. That costs you power, but you have guarantees with regard to timing. You know you're going to take a measurement every 5 minutes or whatever it may be. With the external signals, you often have to leave less stuff on, but you can't necessarily make a guarantee about when your next measurement is going to take place. You're trusting some external event to wake you up. By the way, I'm going to show you some pictures here of, I had a interesting MEng project a couple of years ago where a student and I were thinking about these external signals, and we were making the observation that we were thinking specifically about digital agriculture IoT things, and making the observation that I've developed a few of these in the past, some for grad school, and I noticed a tendency in myself and in many other engineers to, you know, you're working on some system that in our particular case, it was gathering, you know, temperature and humidity measurements around a vineyard. And so as an engineer, you go to the vineyard manager and you say, how often is it useful for you to get measurements of temperature and humidity around your vineyard? Like what is the rate at which it is actionable for you? You probably don't care to have those numbers updated at 10 hertz, because that stuff doesn't change that fast, first of all. You can't take actions that fast. But is every 5 minutes okay? Is every 10 minutes okay? What is the relevant rate here at which you would like measurements? And it's often the case that you talk to these folks and they'll say something like, I don't know, every 15 minutes. And then the inclination as the engineer is to say, okay, to the microsecond, every 15 minutes, I am going to deliver you a measurement. When it's often the case that what they actually mean is, I don't know, on the order of tens of minutes. If I got a measurement every 15 minutes, great. If the next one came 20 minutes later, okay. If the next one was separated by 10 minutes, that's kind of fine. So the answer, I was noticing, I was interpreting it as a requirement that was highly sort of precise, when in fact it was much less precise than that. And so the student and I went through this, I think, kind of a fun exercise. We were considering these latching circuits. So the latching circuit that I'm showing you here, this is a mechanism by which you can turn the microcontroller off. All systems are off. The thing is essentially dead. And you trust something external to wake you up. Some external current source is going to come in and turn on that transistor, which through a series of events will allow for power to return to this thing and wake itself up. And then by way of its GPIO, it can kill itself again. And so we went through this exercise of standing and staring at vineyards and orchards for a while and trying to determine, are there any processes occurring here that happen at about tens of minutes rate? Any natural process? Do we get a strong gust of wind every 10 minutes or so? You know, there's a few of these things that you might imagine. The one that we noticed and ended up building a little device around was there was a bird feeder there. We said, you know, a bird comes to that bird feeder about every 10 minutes. And then I happen to know, because I have a bird feeder hanging outside my window at my house, that when the birds go to sleep, the flying squirrels start coming. And they come, I don't know, every 10 minutes or 15 minutes or something like that. And so the device that we made, it included this circuit, included a microcontroller, and there was a sensor over here that the microcontroller was using to log data. This external current source was a little piezo built into the bird feeder. So the idea was the bird arrives or the flying squirrel arrives, it pecks it, it generates a little bit of current that wakes the system up, it takes a measurement, and then it goes back to sleep. And so one way of thinking about this is effectively we are replacing the internal timer peripheral with some sort of natural timer peripheral. Our timer became the birds. And that means we can't make a guarantee about when the next measurement is going to take place, but we can kind of make a statistical guarantee of some kind. We can say, you know, watch the bird feeder or study it over here, and they come at about the rate that you care to gather measurements. And so though we can't make a guarantee about when the next measurement is going to arrive, what it affords us is the ability to make our low power mode really low power. which perhaps extends battery life very, very long, or with the addition of a little solar panel, perhaps indefinitely. And he gathered some interesting plots of this that I'll just show you. So this is some data gathered from a power meter. This is Michael Awad, by the way. This is his work. Data gathered from a power meter. This is the RP2040's power consumption, toggling between sleep mode, as described in the data sheet, which we'll look at in just a second, and awake mode. So you can see, on the order of maybe 15 to 20 milliamps in sleep mode, on the order of 45 milliamps in awake mode. This is the same experiment running, but it's latching itself off between wake cycles. And what you can see is when it's off, the amount of current consumption is so small that it doesn't resolve really here at all. It's very, very close to zero. It's probably down in the picoamps. Anything else to mention about this? I don't think so, except to just mention that that is a fun experiment to go through, to look at some place and try to identify, where are the timers? And that leads to some interesting thoughts about, like, can you find information transporters? Maybe I don't need to use a radio. Maybe there's some natural system that's moving data in ways that I could sort of tag onto. Right? So it's a fun way to look at the natural world through this sort of computational lens. In any case, so you're trying to get a really low power mode. Once you wake up, you want to get back to sleep as quickly as possible. And while you're awake, you also want to spend as little power as possible. You're, of course, going to be spending more than when you're asleep, because you have to actually turn things on to do stuff. But you want to do that stuff, turning on as little as you possibly can, and turning on the lowest power peripherals that you can that will accomplish the job in the least amount of time. And then you want to get back to sleep. So what this implies is trying to do things in parallel, and also trying to optimize your programs in much the way that we did for the Galton board, not to maximize the number of balls falling through some computer graphics animation, but instead to minimize the total amount of time that we're awake. And this involves, there's a whole bunch of stuff that this could involve, right? This is an optimization problem that perhaps involves a whole bunch of different systems on the microcontroller. I just wanted to point out a couple that we've talked about previously in class, in part because I think this whole exercise of power reduction, it's an interesting exercise in that it synthesizes a lot of the stuff from this whole class. In order to do a good job of this, it's really helpful to know all the stuff that you all have learned throughout this class. For instance, it's really helpful to have some comfort with DMA channels so that you can do some of your information movement in parallel with the CPU stuff that you have to do while you're awake, again, to get back to sleep more quickly. It's also generally the case that if you can accomplish your tasks more so with DMA channels than CPU, so that you can keep the CPU on for less time, these are generally less power hungry, right? And so it may be the case that you can make your awake power consumption less through strategic use of things like DMA channels. And then the programs that you write, you want for those to run as quickly as you can manage, again, so that you can get back to sleep as quickly as you can, which implies a lot of the stuff that we talked about in the Galton board lab. It implies thinking about doing arithmetic quickly, perhaps by way of fixed point in the event that you don't have floating point hardware in your device. And it implies some thinking about those calculations that you're doing. How accurately do you need to compute whatever it is that you're computing? Do you have to know some quantity to 0.001%, or is plus minus 10% okay? In the Galton board lab, for instance, you may remember that we were computing the distance between the peg and the ball, and we made the observation that for our purposes, 5–10% is good enough for us. So rather than computing an expensive root sum of squares to get that distance, we use that alpha max beta min algorithm, which is much faster at the cost of some accuracy, but for that application, that was perfectly okay. And it's often the case for these sorts of things as well, that you can ask these questions about how well do I actually have to know whatever it is that I'm measuring or whatever intermediate value that I'm calculating. And it may be the case that similar optimizations exist that allow you to trade accuracy for time. In the Galton board lab, we were making the trade of accuracy for time to maximize a computer graphics thing. In this case, what you're really trading is accuracy for time, because time means power. So you're trading accuracy for power. Interesting way to kind of think about it. This, again, I mentioned previously, this was assembled for a slightly different audience from you all. So this is information that you all now are aware of. So I don't feel like I need to talk about it. But you guys know what DMA is and why it's useful. And you guys know what fixed point is and why it's useful from previous lectures. And for that other audience, I also suggested a few things that you all got exposed to in Lab 2. Things like the alpha max beta min algorithm, that would trade accuracy for speed, accuracy for power. For this particular audience, it's helpful to point out that multiplying and dividing by powers of 2 can often be optimized away by shifts, exposing them to that operator. Context switching comes with overhead. Pretty code is not necessarily fast code, and for these applications, you often want fast code, not necessarily pretty code. And in most cases, not the RP2040, because we have the hardware divider, it's generally the case that divides are expensive. So let's see. Any thoughts or questions about any of this stuff? Let's look at the data sheet here quick before I move on. So for the RP2040, let's just pop this up. I want to look first at that chapter on power control. This is a short little chapter, but it describes how to put the system into what they call sleep state. You put the system into sleep state by sleeping both of the processors. There's an instruction by which you can tell the processors to go to sleep until some event occurs or some interrupt occurs. And it will go to sleep furthermore if there is no DMA channel running. It wakes up directly from an interrupt. My understanding here, yeah, we do have to, there's a series of registers by which we put the system into sleep state, and then it will wake automatically. Anything to say about this? I don't think so. A slightly more interesting state here, I think, is dormant. This is one I was alluding to earlier. In dormant, it's a zero dynamic power sleep state. So that is to say your power consumption is pretty much constant when you're in dormant mode. All of your clocks and oscillators are disabled. There are two ways by which you can awake from this state. One is by way of a GPIO event, some high or low trigger on a GPIO, or alternatively by the real-time clock. And as I mentioned, waking from the real-time clock from dormant state requires that that real-time clock have an external oscillator. That oscillator can be as low frequency as 1 hertz. It is your responsibility if you're entering the dormant state. I'll show you some code here in a moment, but it's your responsibility to turn off the phase lock loops before you go into it. And then when you wake back up, it's your responsibility to turn them back on again. So you have to be responsible for turning some of this stuff off. But then once you're in dormant state, let's see. I'm going to find that table again. I think they have a power consumption measurement in dormant state. Let me see if I remember correctly. Power consumption. Dormant. Typical average current in dormant mode is 0.18 milliamps, 180 microamps. By the way, is low. In an application where you really, really want low power, there do, of course, exist microcontrollers that have been optimized for such things. The CC1310 would be an example of that, where a lot of thought went into trying to make the low power mode of this device really, really low power. The RP2040 does not appear to have been optimized for that particular thing. But even so, you can get a pretty darn low power mode out of this thing. Bruce? You do. So I believe you do. Let me see. I think they had some demo code up here in the power section. Sleep, dormant. So this is an example of a function that will go to put you into dormant mode. Are they explicitly switching to the ring oscillator here? Configuring the event under which we would like to wake. Doing a quick check that it's a valid GPIO. Figuring out which GPIO event we'd like to wake from. Initializing that GPIO. Making it an input. Associating the dormant interrupt with that GPIO event. And then go dormant. Presumably under the hood that would be, I have to imagine it would be doing that. And by the way, for power consumption, this is another thing that's worth knowing on the RP2040 that I think I mentioned previously. There exists in the RP2040 a ring oscillator in addition to the phase lock loops. We talked a little bit about this when we were talking about the boot sequence. You may remember from that conversation that this ring oscillator is a clock that is composed of a sequence of inverters, right? So it's just flipping voltages, which will generate a clock. The frequency of that clock, however, is a function of the process that's actually running on the CPU, the temperature, and the voltage. You turn the temperature down, the ring oscillator speed goes up. You increase the voltage, the speed goes up. So you can't make guarantees in the same way that you can with, say, a phase lock loop about the exact frequency of that clock, which would make interfacing with things like, say, a VGA screen tremendously difficult or perhaps impossible, because the VGA screen demands very precise timing on its data lines. But in the event that your system doesn't have such requirements, the ring oscillator is far lower power than the phase lock loops, and so perhaps it's the case that you could run your IoT application, for instance, without ever even turning on a phase lock loop and just running off the ring oscillator. It's also a nice source for random numbers, right? As you might imagine, because it has a frequency that's a function of environmental conditions. Nature's really good at being random. And so if you're looking to bring some entropy from the natural world into your device, the ring oscillator is a mechanism by which you can do that. And in fact, I think in the latest SDK, there's a true random number generator that uses the ring oscillator to generate true random numbers. So this is not rand, like pseudo-random numbers. This is a true random number generator bringing entropy in from physics, essentially. There's also, I had a former student investigate this pretty thoroughly, and I included some of his documentation here as well. Demo investigated this a bit as well. Okay. And then, of course, right, it may be the case that in addition to spending power, you're also gathering power. Let's see, where are we? Maybe the case that in addition to spending power, you're also gathering power. More often than not, the way you're gathering power is by way of a solar cell. But this too, if you are deploying yourself in some environment, it's a fun exercise to look at that environment and try to identify the sources of power that you might tap into in that environment. Some of them are obvious, the sun. Some of them are a little bit less obvious and a little bit harder, perhaps impossible to extract energy from, but it's interesting to think about nonetheless. But more often than not, these devices have little solar panels on them. All that I really wanted to say about solar cells and solar panels is that they're generally characterized by their IV curve. So each of these curves represents the current that will come out of a solar cell when you are at different voltage levels. And so what I want to just point out to you about this is that these IV curves generally have this shape, generally sort of flat, and then there's an elbow, and then it comes down. remember that power being the product of current times voltage, right? That suggests that the place where you want to be operating your solar cell is generally right at that curve, because that's where I times V is highest. And so that suggests a need for a little control loop that is observing the amount of power coming out of a solar cell and changing the load a little bit, right, to affect the voltage here just a little bit, and move around to try to keep the solar cell right at its maximum power point. Now you can build these things, but more often than not, folks will, if you're actually building one of these things to like deploy for an experiment or something like that, there exist little maximum power point tracker integrated circuits that will interface with your solar cell, and again, sense the amount of power coming out of the solar cell and then change the load a little bit to try to keep that solar cell right at its maximum power point. It's this link here. Let's see. For instance, maximum polar. Thoughts about this? I don't think anyone's using solar cells this year, but you could imagine that, you know, if you've really gotten obsessive about your low power modes and your sleep-wake cycles and so forth, such that you drive your average power consumption really, really low, it is the case that you could make a device that does not have a long lifespan, but that is power positive, has, from a power perspective, an indefinite lifespan. It'll die eventually, but not because it ran out of power. This is how, for instance, spacecraft work, right? They have to be designed to be power positive because you can't go recharge it, plug it into anything. And so they're designed such that the energy that they gather from the sun when they're facing the sun, in the event that they're going around the Earth, exceeds the amount of energy that they spend when they are out. You could imagine designing systems like terrestrial systems like that as well, such that they remain power positive. And then, at risk of being a little bit silly, you know, like I said, it's just fun to look at an environment and ask yourself, where does the energy live in this environment? And I'll just make the observation that if there exists a gradient, if things are changing from one place to another place, there exists, generally speaking, some energy that might be extracted, maybe not super efficiently. But for instance, if there exists a very large temperature gradient, wherever it is that you're deploying these things, there are mechanisms by which you can extract energy from a temperature gradient. Now, I don't know what exactly this would look like. Maybe you're making a little floating device that floats on the surface of one of those Yellowstone ponds. It's basically at boiling point, and 2 meters up there, it's at freezing. I don't know. So there's a big temperature gradient. Maybe you can get some energy out of it. Pressure gradients. I am not aware of any devices that extract energy from this particular gradient, but what got me thinking about this is, I mentioned previously that I love engineering, but I like a lot of other things too. One of those other things I really like is whales. I think they're really interesting. And they're hard to study because they go very deep underwater. Many of them, though, sperm whales being an example, when sperm whales hunt, they hunt at like, I can't remember exactly. It's an unbelievable depth. They go down and hunt squid, like really, really deep. What that suggests is they start up at atmospheric pressure, they're diving down to an extraordinary pressure, and then they're coming back up. In principle, you could extract energy from that pressure gradient transition. You could imagine something getting squeezed, getting some energy out of the squeeze, and then releasing and getting some energy out of the release. I don't know exactly how that would work, but there is energy there that might be extracted. Magnetic field, you can extract energy from magnetic field. It'd be pretty darn challenging to extract any energy from the Earth's magnetic field. It's pretty weak. But if you're at Jupiter, oh baby, does that thing have a magnetic field. Even if you're on a moon of Jupiter, it's so strong that you could presumably power your system just by having a loop of wire on it and kind of moving a little bit, generate a whole bunch of current, and power your system off of that. Gravitational potential, I don't know, maybe if you're around like a black hole, there's a really strong gravity gradient, maybe there's some energy to be extracted there. Chemical gradients, of course, you know, inside of a battery, there exists a chemical gradient that is sort of maintaining the energy of that battery. Maybe radioactivity, I don't know. I'm not aware of any device that works like that, but possibly. The other fun thing to do, let's suppose that you're building a device for deployment in a place that, that there aren't many gradients. An example of this might be like the very bottom of the ocean. And you're not around one of these hydrothermal vents. It's just dark and cold, and there's nothing. There's not a lot of gradients from which you might extract energy down there. But there's some consolidations of energy down there in some very, very big animals, Greenland sharks and stuff like that. And so maybe this is just science fiction, but maybe you could deploy an event that extracts a little bit of energy from these great consolidations of energy that live in the environment that you happen to be visiting. I don't know, can you convince a Greenland shark to occasionally tug on your device and give it a bunch of energy that you could run off of for a while? If you're deployed in like the high Arctic, there's not a lot of gradients up there. There's wind, I suppose. Maybe that would work. But you know, if you're up there when it's dark all the time, not a lot of energy, but tremendous consolidations of energy, again, in some really big animals. I don't know, maybe you could make your device an interesting plaything for a polar bear, and if you get a polar bear to pull on it once every 2 months, maybe that's enough energy to run your device for that amount of time. Maybe people, I don't know, let's suppose you were trying to measure something, I don't know, in a city. You could design a device that wakes up every X number of seconds or minutes or whatever and takes a measurement. What if alternatively you designed a device that had a big red button on it with some text that said push the button? How frequently do people walk by and push the button so that the people are your timer, so to speak, kind of like playing the role of the birds in that previous project that I mentioned? To what extent do those statistics change if you say don't push the button? Do they go up or do they go down, I wonder? And then this is just getting into fun science fiction stuff, but of course there are less frequent events that are massively energetic, that if you could imagine extracting just a tiny, tiny fraction of the energy of these massively energetic events, perhaps you could run your system for a very long time. I don't know, hurricanes, landslides, volcanoes, tornadoes. I'm not sure exactly even what I mean by that. Take it to the limit. I don't know, maybe you could build Dyson spheres. Some stuff about battery charging. And then the last thing I suppose that I'll just mention about this is the temptation, for me at least, with all these systems is over-engineering them, because it's such a fun exercise to try to like geek out about power consumption and geek out about these various energy gathering mechanisms. It is often the case that the temptation is to over-engineer these systems. In the event that you're deploying one of these IoT devices in a building, for instance, and there's a plug right there, just plug the stupid thing in, right? And so just to give an example of this, I had a couple of MN students a few years ago working on an environmental sensing system for the Johnson Museum. And we went through maybe a week of hallucinating various sort of energy gathering schemes and so forth and data transmission stuff, and then made the, in retrospect, obvious observation that why don't we just plug it into the wall and communicate over Red Rover, right? These particular students, what they were working on is the museum was acquiring a really interesting piece of art that it was a sculpture made of wax. Wax is a substance that requires, you know, you can't have it in temperatures that are too hot, or, you know, it needs a certain range of temperatures and humidities and so forth. And so we were working on a system that would allow for real-time measurement of that system so that in the event the temperature started to deviate, corrective action could be taken. Or perhaps ultimately a closed-loop system could be built around it to keep these things in safe environmental conditions. They did a really nice job with this. Okay, I think that's all I have today. Any questions about any of this stuff? Like I said, I like this topic for the end of a class like this, because this is one of those things that involves everything on the microcontroller. And so once you've gotten exposed to all the different peripherals and you have some understanding of how it works, you can go through an exercise like this in a really, really informed way. And it exercises all the stuff that we've talked about through the whole semester. It's a lot of fun. Okay, I will be in lab this afternoon. I'll see many of you there. I'll see the rest of you on Monday. One, two.